Hello everyone, my name is Sungjae Ohn. I'm third year PhD in CPAS. Today I'm going to talk about three-terminal modeling and EMI mitigation strategy for full silicon carbide UPS. Uninterruptible power supply is used for critical loads such as data centers and hospitals. With silicon carbide MOSFETs, the efficiency can be increased up to 98% for AC to AC conversion. However, fast switching of silicon carbide increases the output common noise. It may interfere with your auxiliary circuits, and EMI standards as IEC strictly limit EMI emission. The standard specifies that limits should be met in worst case of mode of operation, but impact of DC-DC stage has not been covered in most of the literatures. The goal of this modeling and work is to provide design guideline during design phase to mitigate the noise including DC-DC stage. Based on the model, we can predict how DC-DC converter will change the EMI. First, what you see is the common voltage output of rectifier. With the cancellation with inverter, all the low frequency components are decreased a lot. In the other hand, your DC-DC converter may create lots of common noise. The difference could be large at low frequency range. Also, there's 10 dB difference in the slope. Secondly, there is multiple resonance present on the battery side path. At low frequency, your DC inductor and parasitic capacitance of the battery rack resonates. And when frequency goes up, the self-resonant frequency of DC inductor exists. Lastly, at very high frequency, the EPC of your DC inductor and small parasitic inductance of your battery housing resonates. So these two factors together highly deteriorates the CM-EMI when DC-DC converter operates. Experimental results are shown here. Compared to the mode when only AC-AC stage operates, high increase has been observed especially near two resonant frequencies. To verify the impact of parasitic capacitance, two cases are compared. Red one is with 10 nanofarad, green one is with 1 nanofarad. You can see that there's lots of change in noise profile between 150 kHz to 500 kHz. This is the picture of 20 kW prototype UPS. 1.2 kV 40A full silicon carbide NPC module from Microsemi has been used to build the AC-AC stage. We designed the gate driver and fully tested its functionality. On your left, 3 modules serve as the inverter. And on the other side, 3 modules serve as the rectifier. One benefit of the 3-level DC-DC stage is that we can share the same NPC phase lag. It's located in the middle of the UPS. Based on the load simulation to achieve 99% efficiency per stage, the switching frequency is set to 60 kHz for both DC-DC stage and AC-AC stage. There are 2 DC inductors as the balancing technique for the noise. At this high switching frequency range, your DC link capacitors take a lot of volume and deteriorate the power density. We have developed a PWM scheme which reduces common voltage and also compensate low frequency ripple of neutral point voltage on output differential voltage and output common voltage. With this PWM scheme, we can reduce the DC link capacitors to 140 microfarads. All the filters for AC-AC stage are located in the first floor. The inductance value for 2 inductors in LCO filter are 90 microhenry and 50 microhenry. This is the waveform of load side current. Phase A, Phase B, Phase C, and the output voltage of Phase A inverter. as DC link is 800, the switching voltage varies from 0 to 400 or to minus 400. This is phase A, B, C current, and the THD of the load current is 2%. This is the waveform of output capacitor voltage, and this is the waveform of first inductor in LCR filter. The THD of output capacitor voltage is around 1%. The THD of inductor current is around 7%. This is the waveform forms when UPS works in back-to-back conversion mode. Green line is DC link voltage. It stays at 800. Pink is output capacitor voltage. The yellow and sky blue is the output current of rectifier and the inverter. Thank you for watching video.